Hi, my name's Jo Morgan. I'm a maths teacher and today I'm going to talk to you about teaching angles in polygons in depth. Now, in this workshop, we're going to talk about various aspects of this wonderful topic. I love teaching anything angles related, and angles in polygons is no exception. We're going to start by talking about what's on the curriculum. We're going to talk about how angles in polygons is assessed in GCSEs. We're going to talk about some of the key concepts and vocabulary. We're going to look at lots of different methods and pedagogical approaches. We're going to look at some resources, and then we're going to finish by looking at how we can add a bit of depth and enrichment to our teaching of this topic. So let's start with curriculum and assessment, and I'm specifically looking at the English National Curriculum in secondary schools here. Now, angles is a pretty big strand of geometry in secondary maths. In Key Stage 3 and Key Stage 4, we do a lot of work on angles, and within angles, there are lots of different topics that we study, typically over the course of the 5 years from year 7 to year 11. Now, some of that starts off as being a recap and a deepening of knowledge gained in primary school. So there's the idea of what an angle is, a measure of turn, and then the idea of notation, of drawing angles, measuring them, estimating the size of angles, understanding acute, obtuse, like that's all stuff that's done at primary school. And when students come to us in secondary school, we're recapping and deepening the knowledge they have of those things. Same with those sort of what I call basic angle facts, angles on a straight line, angles around a point, vertically opposite angles. It's all done in primary school, as is angles of a triangle and angles and quadrilaterals, all done in primary school. So when our students come to us in year 7, typically we're deepening that understanding, adding some challenge, but it is recap at that stage. Then we introduce new content in secondary school. We have typically taught in year 8 or year 9 angles in parallel lines, and again typically taught in year 8 or year 9 angles in polygons. Then leading into GCSE, we have more angles content, looking at bearings and then looking at circle theorems on the higher tier. So you can see there's quite a lot under the umbrella of angles, quite a lot of topics, and angles in parallel lines and angles in polygons need to come after those basics are secure. So once students are really familiar with and fluent in those angle facts, then they're ready to tackle the more complex angle stuff. Now, just having a look at what it actually says on the national curriculum, the content is all on the Key Stage 3 curriculum. So in terms of angles in polygons, nothing new is added at Key Stage 4. And we know that at Key Stage 4, students can be tested on any Key Stage 3 content. So this is what they can be tested on at GCSE. So we have that first bit there is about using notations, and really that's about being able to say name regular polygons, so knowing the names of them. Then this bit's interesting in terms of the wording. Derive and use the sum of angles in a triangle and use it to deduce the angle sum in any polygon and to derive properties of regular polygons. So it's specifically saying that you need an understanding of the angles in regular polygons based on the understanding of angles in triangles. So that's interesting that it's quite specific about that, how that to make that link between triangles and polygons. And then the other sort of mention of angles and polygons really comes here where it's saying that applying angle facts and properties of quadrilaterals to derive results about angles and sides, and that's linking in with other bits of maths. So really this is the only kind of specified things that we have to teach, and as usual it's a little bit vague, but you know, we get the gist of it. We basically need our students to know what the polygons are and to understand how to work with angles and polygons. Notice how there is no mention of the word tessellation. I'll come back to tessellation later, but it used to be specified at GCSE, that, or maybe at Key Stage 3 in fact, that students had to know what tessellation is. It's not specified anymore, and that doesn't mean that students can't be asked the tessellation question, but if they were asked a tessellation question, the word tessellation would have to be defined in the exam. So it might explain what tessellation is and then ask, do these polygons tessellate? Whereas it used to be they could just say, do these polygons tessellate, and the student would need to know that word, but they don't have to anymore. Just having a quick look at what exam questions students might be faced with in their GCSE on angles and polygons. this is what I consider a very typical example. So this was actually from the sample assessment materials provided by Edexcel before the GCSE sort of got started, and this is kind of, to me, like an everyday angles and polygons question. It's got a bit of challenge in it. It's not the most straightforward question, but really it's about understanding interior angles, but also using another angle fact that students have learned in primary school, that angles around a point sum to 360. So that's a very typical question. Some other questions that have actually come up in angles and polygons. These two examples are both from AQA. The first one's multiple choice. What's the exterior angle of a regular decagon? And then the second one is a regular polygon has an exterior angle of 20 degrees. Work out the number of sides. They actually both use the same skill. One of them, you could say, is working backwards, and it's a 2-mark question as opposed to a 1-mark multiple choice. So here's another fairly typical GCSE question on angles and polygons. This one's from AQA. This one requires a little bit more reasoning and also a good understanding of vocabulary, because if you look at that question, there's a lot of technical mathematical vocabulary in there. We've got the word congruent, identical. Students need to know what that means. We've got the word regular, we've got the word polygon. Okay, so we know that the two polygons have been joined together. And actually what's really funny here, it says not drawn accurately, but I'm sure lots of you have seen students who try and solve this by carrying on the diagram, and I've definitely had students do this in the past, sometimes with some success, which it shouldn't be that they can do it that way, but sometimes they manage it. And yeah, they literally, you could see them kind of drawing the other sides in and then counting those sides. But actually, if you look at this question, it does take some reasoning, because first of all, they need to know that if they do 360 to take away 60, then they end up with the 150 for each of the interior angles. So they're using an angle fact. They're also using the fact that the polygons are congruent to know that they can divide the 300 into 2. But then once they know the interior angle's 150, then there are a couple of different ways that a student can then work out the number of sides. So I would do it, if I know the interior angle is 150, I would then find the exterior angle, and then I know how to get the number of sides. But actually what that brings you to is another way of doing it, because actually what you could do is bisect that 60, immediately know the exterior angle is 30 and do it from that. So this is actually a question with multiple methods that work and are all equally good methods of doing it. But all these methods require a couple of different angle facts or bits of knowledge. So there's reasoning, but there's also, you can't do this without some knowledge of angle facts. Another example from AQA, this one's foundation tier, and this one is about critiquing methods. And actually, angles and polygons is a topic that's often used for these method critique questions that the examples need to include. So here, she's working out the interior angle of a polygon, and she said it's 360 divided by 8. Is her method correct? And you have to explain. And there's various different explanations that would be acceptable there. Just a slightly more challenging question I wanted to show you. This one's from the Edexcel linked pair pilot. The linked pair pilot was something that happened, I don't know, maybe about 7 or 8 years ago, and it was before the new GCSE, which kind of put an end to it. But there was this pilot, and my school was involved in it, where we were trying to assess maths in a different way with separate GCSEs in methods and applications, and the questions were challenging, and they weren't all challenging, but there were some really great questions in those pilot papers. This is one of them. So we have a regular pentagon, we have part of a regular octagon drawn, or that takes a bit of thinking to kind of see that octagon, and we have a parallelogram, and the question is asking us for the angle the angles in the parallelogram. So that takes, again, some reasoning, lots of knowledge of angle facts. Final exam question I want to have a look at, again, is from Edexcel. This is a 5-mark question, which is a pretty big question. And I've got a bit of the examiner's analysis for this one. So have a look at this. We have a pentagon, and we're told that there's 2 unknown angles, and one of them is double the size of the other one. And so we want to work out the size of angle BCD. Now, I look at this question and I think, well, this is really testing 2 things. First of all, do we know the angle sum in a pentagon, which is basically testing knowledge? And then, do we know how to work with that information about those missing angles, about one of them being twice the size of the other one. And we know that you can either use a ratio approach, so splitting the sum of those two angles in the ratio 2:1, or we can use an algebraic approach, setting up an equation. Either way, this is really testing two skills, but you can't do the ratio and the algebra bit unless you know that angle sum. Here's actually a model answer. Well, I say a model answer, it's a student exemplar answer provided by Edexcel, so this is an actual student's work. A couple of things I really like about this. I like the way the student has written 1, 2, 3, 4, 5 on the sides. It's showing that, I reckon this student's teacher has shown them a sensible way to make sure you've counted the sides correctly. So normally I kind of do a little dot or something. In fact, I'll tell you what I do that isn't good. Sometimes I do a little line on each side as I count them, and that's not good because that looks like a hatch mark, which makes it look like I'm suggesting the sides are the same length. So I shouldn't be drawing little lines on each side as I count them. And actually this is much better to actually write 1, 2, 3, 4, 5 around the outside to make sure we've counted the sides correctly. So whoever that student's teacher is, or if it was the student's idea themselves, that's great. What a nice way of sort of ensuring that accuracy and systematic approach. I really like that. The students drawn a line across it, which I guess they then realised wasn't necessary. But then if you look at their working, they've got this method for working out the angle sum. They haven't memorised it's 540. They know it's n-2 times 180, so they've worked it out. Then they have subtracted the angles they've been given. They know that that little square means right angle, and they've ended up with the two angles that are unknown, summing to 210. And then they've used an algebraic approach and they've solved the equation. Now, that is a full 5-mark answer there, really nicely done. This student knows their stuff. They know angles in polygons, and they know how to solve this equation. So that's fantastic. They actually get 2 marks just for knowing the 540. And then the remaining marks, there's 2 marks for showing a method to split the remaining angles 2:1, and then there's a mark for the final answer. And interestingly, if they've not got the angle sum right, if they'd not got the first 2 marks for the 540, but they had used an angle over 400 as the angle sum and then done their correct method for kind of solving the equation, then they would have picked up a couple of marks. So, you know, but only if it was over 400, the angle they used for the angle sum. So that's interesting. I'm not sure, perhaps there's a reason for the 400 there. Because actually, if you look at this student's response, this is a real shame, because this student has done absolutely lovely workings and absolutely brilliant equation solving, but they've used 360. And that means they've got 0 marks for this. If they just used an angle over 400, even if it was the wrong angle, they would have got some marks there. But because they've used 360, and I suppose that's what Edexcel are trying to avoid. They don't want anyone to think that the angles in a pentagon add up to 360. But does seem frustrating that this poor student's got 0 marks, because look at the rest of their workings. It's actually lovely. They've written it out as a fully formed equation, the 3 angles that are known, the 2 angles that are unknown. They've expressed it algebraically, which is quite a good skill to use. They've put that all equal to 360. They've simplified, they have solved well, and their answer unfortunately is wrong, even though they've correctly found the right angle using their answer. Unfortunately, it's wrong because that original sum of the angles was incorrect. That's quite frustrating to me, because this student has shown some strong understanding of a mathematical approach to solving this question, but because that one number was wrong at the start, unfortunately they have scored 0 marks here. It says in the examiner's comments that actually one of the common mistakes was assuming that the angles are up to 360, so that's a real shame. But also some other things that I'm sure experienced teachers would have seen before, which is where students assume that some things are equal. So for example, assuming that 125 at the top is equal to that 2x at the bottom, or that quite often students assume that angles are equal. I think they do a lot of work on isosceles triangles, and so they have this kind of default where they look at a diagram and they think, oh, these two must be equal, when there's nothing in the question to say they're equal. So that is something that students quite commonly get wrong. So that's it for looking at curriculum and assessment. Let's have a look at some of the concepts and the vocabulary. This is a topic with lots of technical vocabulary, and we need to spend time. I'm not necessarily saying we need to start the topic with a lesson on vocabulary, but interwoven through our lessons on this, we need to be very clear about the vocabulary, because lots of this is new to students. Even the word polygon. So the word polygon might be new to students in that they will have heard the word shape many times, but they need to know that a polygon and a shape are different things, because a polygon has straight sides and the shape could include, say, a circle. So it's wrong to say polygon's just another word for shape. We mustn't say that, because polygons have straight sides. It's actually really interesting to ask students to try and get them to understand what the word polygon means by asking them what the word poly means, because they will have heard that in other places. I showed my students this slide that I found this on the internet, and I showed them this, and I said, you know, we've got polyamorous, many lovers, we've got things like polynomial, many terms, and then we talked about, and I asked them anywhere else they'd heard the word poly, and they always give me the answer polytheism, which is belief in many gods, I believe, and they've all learnt that in RS, which I always go and say to the RS teacher, you know, good work, because they all knew that. But it's worth drawing attention to this word poly. It's a key part of a word in many subjects, and our students need to know it means many. Oh, this was nice. I then said to my students, so what do we think polygon means? And you can probably guess, a lot of them said, oh, is it many sides? And it's like, no, it's not many sides. What do we think gon? Do we think gon is like sides? And we had a good discussion about what else it could be, and the students then ended up suggesting the correct answer, which is many angles. Polygon, many angles. Now, I have my students write down the definition of keywords. I know some people do that in a glossary, say at the back of their books, or even in some cases in a little separate, one of those small little vocabulary books. Some teachers have their students write down kind of a mathematical dictionary. I don't do that. I just have them highlight in their notes keywords. But what was interesting was when they wrote this one down, I said to them, you know, we're going to have to talk about this definition, because like a lot of definitions in geometry, the words just aren't that helpful. Closed 2D shape with straight sides. They don't know what closed is. They might know what 2D is, but I got out a prism out of my drawer on my desk, and I said, right, this is 3-dimensional, and we really need to exemplify these things. Don't just assume they know what 2D and 3D means, and certainly don't assume they know what closed means, because they've probably never heard that in terms of the definition of a polygon. What do we mean by closed? So in maths in general, it's not a good idea, particularly in geometry, to give a worded definition with no exemplification. So it's a good idea to give examples and non-examples to help bring that definition alive. This is one I found online, and I showed this to my students. The following are polygons, and for each one I said, it's got straight sides, it's 2-dimensional, and it's closed. It has no gaps in the sides. So I said that for each of them. Look, 2-dimensional, straight sides, closed. And then I say, and these aren't polygons. Look at that first one. It is 2-dimensional. It does have straight sides, but it's not closed. And same with the second one. It is 2-dimensional. It has straight sides, but it's not closed. There's a gap in the sides. It's not a complete perimeter. There's a gap in it. And the next one, it is 2-dimensional. It is closed, but it's got a curved side. The sides have to be straight if it's going to be a polygon. So I'd literally verbalize with each one of them why or why not it's a polygon. And by doing that, I'm repeating that definition enough. So each time I'm sort of referring back to that definition. Now, I'm not going to read all this out to you now, but I just wanted to draw your attention to it. Foster77.co.uk, Instant Maths Ideas. This is work done by Colin Foster. He has a pack for every topic on interesting things to discuss with your students, interesting task ideas, misconceptions. They're fantastic. So I had a look at the angles pack in preparing this presentation. This was quite nice. He talks about how this topic, angles, contains a lot of definitions, and he talks a bit more about how teachers should approach this. And he says you've got to be careful if you say something like a polygon is a shape containing straight sides, and then the teacher draws on the board a circle with a load of straight sides in. And you know, it's about really pulling apart those definitions, finding gaps in definitions and saying that definition, you could draw this and that's not a polygon. So I'm not going to read all that out now, but it's worth looking at Colin Foster's stuff on this. In fact, all of Colin Foster's stuff, the Instant Maths Idea material, are so helpful when planning lessons. I recently, a colleague of mine taught angles and polygons to a top set, and she kept saying that she didn't know how to challenge them because they already seem to know the angle rules. They already seem to know how to work out the angles in a polygon. And she was just looking for all these hard questions all the time. Now, in preparing this talk, I found loads of other ways you could have challenged them. And I think one thing, now I'm not suggesting that every class needs to know all the different types of polygons, but if you've got a really smart class who are racing ahead, instead of accelerating them onto the next topic, instead, why not spend time enriching their knowledge of maths by talking about the different types of polygon? You know, we've got convex polygons, concave polygons, complex polygons that intersect, the sides intersect each other. And yeah, these are things that if you were just doing a normal curriculum without any enrichment, without going above and beyond anything, you probably would never meet convex, complex and concave polygons. But if you've got a class who are racing ahead and you're looking for ways to challenge and enrich them, then yeah, talk about these things. You could spend a lot of time looking at really interesting types of polygons like these. Now, regular versus irregular is something that all students need to understand. And, you know, that can be exemplified pretty easily with things like this. A regular hexagon, this is what we all think of when we think of a hexagon. Our experience at primary school of hexagons may have mainly consisted of pictures of regular hexagons, but we need to make sure they know that irregular hexagons have 6 sides, but don't look like the regular ones because the sides can be different lengths and the angles can be different. So it's helpful to talk about the definition. Regular means same sides and same angles, so same lengths, all sides are same length and all angles the same size. And irregular means that one of those things or both of those things is not true. And I think it's whenever in any topic, if I draw a shape on the board, or let's say I'm doing area in year 7 and I do L-shaped areas. So I'm saying, right, here's an L shape, let's say, and I'll say, well, I'm calling it an L shape, but let's check what it actually is. I'll count the number of sides and I'll say, oh, it's an irregular hexagon. And they're always a bit taken aback by that because that's not what they think a hexagon is. But I always do that. Whenever I draw an L shape on the board and say area, I'll always actually say, well, what shape actually is this? Let's not call it an L shape. Let's say what it actually is. So that's something that I think is worth doing throughout your teaching. Now, regular polygons versus irregular polygons. I found this online and I like it, but I kind of don't like it in a way because I like the way it shows, right, this is what our regular polygons look like and here's what our irregular polygons look like. What I don't like is the use of scaling triangle and rectangle there as if they're the only irregular 3-sided and 4-sided shapes, whereas we know that an isosceles triangle is also an irregular triangle. It doesn't have to be scaling to be irregular. And we also know that a rectangle is definitely not the only type of irregular quadrilateral. So, you know, we could have drawn any quadrilateral that's not a square there and it would have been irregular. So I'm not a big fan of that. But what I do like is putting them side by side and to really emphasize the idea of this is what the regular ones look like and the irregular ones could kind of look like anything else. Basically, as long as it's got that number of sides, anything else. And actually, it's quite funny because whenever I try and draw one on the board, an irregular polygon, I find it really hard to draw. It's like, right, I'm just going to draw an irregular octagon on the board, and then I try and do it, and either it ends up looking regular or it ends up with the wrong number of sides. So it's actually harder than it sounds to draw an irregular polygon. It might be something that's sort of fun to ask your students to do. Can you draw an irregular hexagon? Have a go on a mini whiteboard. Let's see. You're going to have different ones. But one thing I wanted to draw attention to here was the vocabulary, where the names of the regular 3-sided shape and the regular 4-sided shape are the only ones where we have a special name for them. Yeah, so we call a regular triangle. We would not say regular triangle. We would say equilateral triangle. And we would not say regular quadrilateral. We would say square. Okay, so everything else, we just put the word regular in front of the polygon name. But for those two polygons, we do have a special term to describe the regular ones. And actually, I'm not going to go into the history now, but there's all sorts of interesting things. If you look back through the past, through old textbooks, you can see variation in what we call those things. But now these are pretty well-established terms, equilateral triangle and square for the regular polygons of 3 and 4 sides. A Freyer model or Freyer diagram is quite a good thing to use in geometry particularly, because geometrical terms are not well defined by words, they're better defined by examples and non-examples. if you are someone that uses Freya models or something you're thinking of using, this is a good example. And you could get students to fill these in themselves with their own list of characteristics, their own examples, non-examples, and then finally their own definition. So they can fill these in themselves, or you could present them with one and you could sort of analyze it. But yeah, Freya models are really good for this kind of vocabulary. Polygon naming is so interesting, and this is definitely worth spending some time on. It's some schools have a quad in them. Not all schools do, unfortunately, but if a school has a quad, it's a 4-sided courtyard. And you can talk about the word quadrilateral, also quadratic. And it's funny, isn't it? Because quadratic kind of, you think of quadratic has a power of 2, not a power of 4. But actually, quadratic is all about squares. So that word quad is an interesting one that comes up in various places. This list here I took from Colin Foster's website, the Instant Maths Ideas material. But yeah, he has a lot of the same ideas as me, or perhaps I got my ideas from him, because I do tend to show a picture of the Pentagon. This is kind of cultural capital building. It's like, it's fine for me to spend a minute of my maths lesson saying, hey, who knows what this building is? That's the Pentagon. Why is it called the Pentagon? Oh, it's the shape of a pentagon. And why was it built like that? Because there's some really interesting stuff about it. So I'm also looking at where do we see hexagons in beehives, because they tessellate, and we'll talk about tessellation later. Heptagons, well, look at a 20p piece and a 50p piece. They kind of look like heptagons, but they're rounded at the corners, so they're actually not polygons. Because they haven't got fully straight sides, but they are 7-sided. I don't think there's anyone in the world who talks about octagons without mentioning octopuses and octopi. And then obviously we have that link with deck and being to do with 10 is really worth mentioning. We have decimal, for example, and that kind of the idea of things relating to 10 is really key in maths. Of course, you can go further. There's no need to go further. Like if I want to talk about a 30-sided polygon, I don't need to know that's a triacontagon. I can just call it a 30agon or 30gon. I don't need to know any words above. I teach my students up to 10 sides, but I do also tell them a dodecagon is 12-sided, because they often talk about dodecahedrons, which they've heard, and it's such a lovely word. They often say, oh, is it a dodecahedron? It's like, nope, I can show you a picture of a dodecahedron. That's a polyhedron. That's a 3-dimensional shape, but actually it's a dodecagon is 12 sides. But yeah, we don't need to show them all this. They definitely don't need to know all this. But the naming conventions are really interesting. And we need to acknowledge that we don't need to bother with these things. I don't need to know the name of a 18-sided shape, an octadecagon, when I can just say it's an 18gun, and that's fine. So we don't need to know about them, but they are interesting. And if you have a curious student in the class, you hope that they would say, wow, what do these things look like? They should say that. If they've got that curiosity, they should ask what these things look like. So you can show them some examples, and why not? Why limit this kind of, let's stick to the curriculum? They don't need to know what these look like, so I won't show them. If they ask in the questions, show them what they look like. Google Images is your friend here. So we have a 14-sided one there, a 50-sided polygon, and a chiliagon, a 1,000-sided polygon. Looks so much like a circle, and actually you'd really have to zoom in on that 1,000-sided polygon in order to see that these are straight sides. That's not a circle. It's definitely not a circle. Those sides are straight. But isn't it interesting to see that as the number of sides increases, it looks more and more like a circle? And then you could have a discussion then about the angles. We can estimate that angle. We could look at that angle in a 14-sided polygon and estimate that it's going to be pretty close to 180, because it's almost straight. It's not straight. And then we could say, well, it's even straighter in that 50-sided polygon. So we could talk about how they're actually becoming closer to 180 as the number of sides increases. I'm not going to show you this now, but you must check it out. It's brilliant. Ed Southall made a video explaining how the names work in polygons. It's a short video. It's less than 3 minutes. I really recommend showing it to your class. It's a lovely little video, and it basically sort of talks about how these bits of Greek words are pulled together to create, say, like 15 sides. Penta comes from 5, like pentagon, 5 angles. Penta means 5. If it's a between 11 and 19 sides, we're going to add a deca, and with some exceptions. But if it was between 20 and 100, we would add a conta. So we can have a pentadecagon or a pentacontagon, and it's really interesting stuff. And I love this. This is really enriching, fascinating stuff. To me, the final bit of vocabulary that really needs some definition is the interior versus exterior angle. And I think interior, like, people know that interior means inside. It's a term that you hear quite a lot in life. Exterior, I think people know that means outside, but actually that definition is quite specific with an exterior angle, isn't it? Where you're basically extending one of the sides, and it's almost like by definition they add up to 180 degrees, like as if that's how we define it. It's the two angles on a straight line that are adjacent to each other. But it does need some time, because actually you do see students getting confused about exterior angles and sometimes thinking it's the whole way around the outside. So that is an important one to define. As with other vocabulary in geometry, it's best defined using examples and non-examples. This is from the website nonexamples.com, and you can see that's an exterior angle, that's an exterior angle, that's an exterior angle, and this is not one because. Okay, so it's worth just taking time, not necessarily all at the beginning of teaching the topic, but when you get to exterior angles, it needs a bit of time on what it actually is. Right, so that's to do with the vocabulary. Now let's have a look at methods and pedagogical approaches. Now, I've written a book, a compendium of mathematical methods, with a whole chapter on angles and polygons. And it was when I was writing this book that I discovered all sorts of amazing ways that we can work with angles and polygons, when I think before I just assumed that it was all about splitting polygons into triangles, and that was pretty much the kind of way that everyone taught it. Like, I've never seen anyone teach it without splitting polygons into triangles, but then I researched it and found out there are loads of different approaches. In the book, I talk about how this is nothing new. So this is an extract from a textbook from 1878, where we have angles in polygons being explained with a proof by the way that looks different to the way that we would currently do it. I mean, this proof totally makes sense. I talk about this in the book, but it's not the way that we currently think about how to find the sum of the angles in the polygons. Just look at the wording there. The interior angles of any polygon are together less than twice as many right angles as the figure has sides by 4 right angles. Less than twice as many right angles, so 180 less, than the figure has sides by 4 right. I don't even know what that means. I think I do know what that means, but I'd really have to think about that. The wording is appalling. Luckily, our vocabulary has improved, and the way we explain things has improved. And I'll show you in a minute a little bit more about this idea of thinking in right angles. They very much used to think in right angles, and now we talk about 180 degrees, whereas then it was all like, how many right angles are there? And everything was right angle based. The first method that I suggest in the book for working with angles and polygons is the exterior angle method. And so if I personally had to answer this question, find the sides of the interior angle in a regular octagon, if I had to work out that answer, I would do it using exterior angles. So that's my chosen method. So I would just do 360 divided by 8 and then take my answer away from 180. Okay, so I mean, to me that is amazingly efficient and crystal clear. So I don't sort of think about, oh, what's the angle sum? I don't bother with the angle sum. I just do it through the exterior angle method. And I like this so much because it's the way I do it, and because I think it's so efficient and so crystal clear, that I last year decided to only teach this method to my year 9s. I did not teach them the n-2 triangles thing. And I've changed my mind now, and I'm not doing that anymore. It was a one-off that I tried that, and I'll talk to you about kind of the pros and cons. In my book, I won't show you this for the whole chapter, but in my book, under each method, I have an opinion. So here I'm saying it's highly efficient. You just need to know 2 angle facts. You need to know that the exterior angle sum to 360 and the interior and exterior angle sum to 180. And I've talked about that you can demonstrate those things in various ways. And I say the disadvantage is that it works for regular polygons, but actually, you know, you can use exterior angles in the irregular polygons, but not to answer a question like this. So yeah, it's got its pros and cons. And when I say dynamic geometry software for demonstrating it, I mean things like this GIF, which is really lovely, which shows that in any polygon, if you bring those exterior angles together, then they meet at a point and therefore sum to 360. I'll talk a bit more about ways to demonstrate it. So these GIFs are good, but they go pretty fast, and you can keep them on the board for a while and get students to look at them and reflect on what's going on. But I would definitely keep it on for a while and just let students sit and mull it over. You know, what's this showing me? What's it telling me? But I do think that the GIFs are a little bit quick. There are perhaps better ways of doing it. I've taken a GIF of this, but actually this is GeoGebra, so you can actually do it at your own pace. And you can see what's happening here is it's different. It's not that polygon is shrinking and we're showing those exterior angles meeting at the middle and adding to 360. In this one, we're actually gathering together the exterior angles and showing that they meet around a point. Okay, and like I say, you can adjust the diagram. You can do this at your own pace because this is GeoGebra. Everything that I'm talking about in the slides, so there's in the comments section, which you can get from my blog, the download of the slides, there's the link. So the link to this is available if you want it. Of course, you don't have to use dynamic geometry, and in fact, if you want to sort of use a demonstration of why the exterior angles of any polygon add to 360, you can do that through paper cutting. You can draw the polygon with the exterior angles, you can cut out the polygon from the middle, slide those angles together and see they meet around a point. It's a demonstration, it's not a proof, but all these things are basically putting that fact into the student's head. You're trying to show kind of why it works, but at the same time, it's memorable to the students, and if you show them something that sticks in their head, hopefully they'll always remember that those angles add up to 360 degrees. My choice of method is the MathsPad interactive tool, which is free for anyone to use. You don't have to be a MathsPad subscriber to get this one. It's a really lovely tool, and this is a still shot taken from it, but it's really lovely. You can have all different size polygons. You can shrink the polygon down, and your students can watch you shrink it down, see those angles meet in the middle. Okay, and then you can say, well, that was interesting. They all added up to 360. Let's try a different polygon. And then you shrink it down and they start predicting what's going to happen. And they're like, this doesn't work for any number of sides. And oh, look, they always add up to 360. And to me, this is really memorable to students. And to spend a bit of time on this. So, you know, I had this up and I was like playing around with it and like, oh, look, we can shrink it and we can look what happens. It always ends up being the same thing. Let's try a different one. You can, on this one, walk around the outside of the polygon as well. I'll talk a bit about that in a minute, this idea of walking around the outside. I think this is really powerful stuff. This is this idea about sort of walking around the outside. You know, this idea of an angle being a measure of term. And this proof about words kind of suggests that if you take a pencil and you put it on the edge of your polygon, and then you walk around the outside of the shape, you basically move your pencil, and each time your pencil turns, it's turning through the exterior angle. So each time you get to a vertex and you turn the pencil to go along the next side, it's turning through the exterior angle. So this is all about that angle as a measure of turn. And what you notice is that by the time you get to your end, your pencil has done a full turn. So it's turned 360 degrees. That's another way of looking at this. Of course, once you know that the exterior angles are up to 360 degrees, you don't need to immediately say, oh, and so now we know the interior angles. You can actually start with questions like this, where you say, well, they all add up to 360 degrees, so what's A and what's B? And that's now a really simple problem to solve because we know what they add up to. So it's worth spending some time on that. In terms of exam questions that this method answers really quickly, stuff like this, it's just, you know, it can be done instantly with this method. So that top one, work out the size of the exterior angle. Oh, 360 divided by 9. It works because that's regular. That's the thing. It's quite annoying to say, oh, this only works in one particular type of polygon, it has to be regular. But it is very efficient if it's a regular polygon. So that top left one, nice and easy. The size of each interior angle is 156, work out number of sides. That's really efficient to do using an exterior angle. Because if I know the interior is 156, I straight away know the exterior, and then I can just do 360 divided by that. Okay, same idea on the one at the bottom. It says it's a regular 10-sided polygon. I need the interior, so I would just do 360 divided by 10 and then take my answer away from 180. So this is a really efficient method for questions like this. However, and I found this when I taught it, this is not such an efficient method for questions like this. In fact, with this one, if you've only been taught exterior angle method, so you've only been taught this idea of 360 divided by the exterior angle divided by number of sides, and then you can get the interior by subtracting from 180, then this sort of question is like, you look at it like, I don't even know if I've got enough information. I mean, you can do it, but it's really complicated. Work out the number of sides of the polygons with these sum of interior angles. if you haven't been shown the n minus 2 times 180 thing, this is way harder than it needs to be. So when I decided not to teach the n minus 2 times 180 thing, I made my students' life harder because they couldn't easily do questions like this. Also, now I know the national curriculum states that I should be giving my students that understanding of n minus 2 times 180, in other words, linking the polygons to the number of triangles, and I hadn't done that because I just taught the exterior angle method. So lesson learned. So moving on to that n minus 2 method. Now this is really commonly taught, as in it's been taught for a very long time, and it's taught by vast majority of maths teachers. And what typically people start this topic by getting students to split up polygons into triangles. And if you've ever taught it, you'll know that they don't always do that as easy as we think they will. Sometimes they're kind of drawing triangles that kind of with vertices in the middle of the polygon, which doesn't work for this particular method. You do need all the vertices of triangles to coincide with vertices of the polygon. And also sometimes students do it in a kind of random way. And you kind of, if you look up the top there, these are all the different ways that you can split a hexagon into triangles, and they all work, but some of them are the same. You know, they're all, we can see here that there are 4 triangles in a hexagon. We only need one of those. We need one of those diagrams to show it, but they're all different and they're all a bit kind of all over the place. But actually we could think a bit more systematically about this. So when I say think systematically, I'm saying that to split a polygon into its triangles, perhaps the best way of doing that is to always start each straight line from one vertex. So you choose a vertex and then you draw a line to each of the other vertices to form these triangles. And that's a much more systematic way. So instead of just like randomly taking a load of polygons and drawing lines and trying to find how many triangles are in them, I'd rather see a systematic approach. We start from this vertex and then we split it like that, which means that it's just you know, mathematicians should be approaching things systematically where they can. But yeah, we do see some mistakes drawn with the triangles, but we also, the other thing is, I think the concept's quite conceptually challenging, that the angles, if you know there are 4 triangles in a hexagon, that you then know that the interior angles of the hexagon is 4 times 180. Now, I get it, but I just don't think it's as obvious as we think it is. You know, I've drawn all the little dots in there to show, here's all the little angles in the triangles. And if you were to draw all those in, you then realise, oh, altogether, they're the same as the angles inside the polygon. So those two things must be the same. The sum of the angles in the triangles must be the same as the sum of the angles in the polygon. But I do think that that's kind of not as obvious as people make out. I think conceptually that's quite tricky to just get your head around those two things being equivalent. MathsPad have another interactive tool which is fantastic for this. This one is part of the MathsPad subscription, but it is it's really clear. I like their use of colour. So here you can see, and this is like you can go through all the different polygons and keep changing the polygon and showing the splitting and adding to the table. But yeah, I just like their use of colour is very clear there. And perhaps it makes it easier to understand that kind of final idea about all those angles together being equivalent to the separate triangle sums. Just to have a look at how this has been treated historically, because like I said, this method has been taught forever. So this is a 1984 Haling's book. And you can see that method really clearly there. Again, though, they have split that triangle by starting from one vertex, as I suggest. That's a sensible way to split the polygons up. We don't want to be randomly drawing lines all over the place. Have a systematic way of doing it. And it says, you know, complete the table, complete it for an icosagon without drawing one, so that's 20-sided shape, and can you do it for an n-sided polygon? So you know, that is classic, and that's kind of how we do it now. Notice how it says don't draw a concave polygon. And it's interesting, isn't it? See what happens if you draw a concave polygon, and you know, you've got to be a bit careful about saying this will always work, because maybe it won't. But yeah, it's I'm just trying to demonstrate that this method has been used for a long time. This is from 1965 from a book called Cornerstone Maths, and again they have done the splitting thing, so they have split up these polygons into triangles. And what's interesting though is the way they kind of explain the rule, and it's here. They talk about it being 2n minus 4 right angles. So it ends up being 2n minus 4 times 90 is the total sum. So whereas we would say n minus 2 times 180, they say 2n minus 4 times 90, which is the same thing, but they're saying, right, if you want to find how many right angles are in a polygon, you double the number of sides and take away 4. And that doesn't tell you the angles, it tells you how many right angles, so then times it by 90. And I think that's fascinating that they used to work in right angles, like I mentioned earlier. One more book, this one's from 1978, Mathematics for Today, and just to show that even then they were still talking in right angles. And I think to me that just seems really unusual because we just don't do that anymore. We don't work in right angles. But again, they're saying the sum of the interior angles of an n-sided polygon is 90 times 2n minus 4, which is the same thing as 180 times n minus 2. It's just a different way of writing it. I think that's really interesting. Also, have a look at the way that that has been demonstrated, because that's actually quite different. There's no splitting up of triangles here. That's been done by using the existing knowledge of exterior angles and then basically doing some algebraic manipulation. So that's really interesting. This is from Colin Foster's Instant Maths Ideas, and he said, right, in a regular polygon, the interior angles are equal. So we have this formula. You do the total angle sum, which is 180 times n minus 2, and you divide it by n, and that gives you each of those angles in a regular polygon. But if you simplify that, you get 180 minus 360 over n, which is the way of doing it with exterior angles. So we got two equivalent formulae that come from two totally different methods, but they're equivalent. Of course they're equivalent, because they're working out the same thing. But I don't want to go through all the methods in my book in detail. Buy the book if you want to read them, but basically there are other ways of doing this. You could do triangles from the centre, so you could always start at the centre of a polygon, draw those, if it's a regular polygon, draw the triangles going out from the centre. They're all isosceles triangle. The angles at the centre are really intuitive and easy to work out. The angles at the centre are just 360 divided by n, and I think every student can see that. And then we have a load of isosceles triangles coming out from that, and from that we can work out half of each of the interior angles. So that's one way of doing it. Another way of doing it is not a point in the middle, but any point in the centre. If you draw all your triangles from there, so you basically split the polygon into triangles, but from a random point anywhere inside the polygon, then the angle sum is going to be however many triangles you've drawn times 180, but then you need to take away that 360 in the middle because you don't want to include those ones. So it actually ends up being the number of triangles, which is n triangles, 180n take away 360. These are all equivalent, but these are different ways of doing it. And as a mathematician, as a maths teacher, these things are really interesting to have a little play with and to wrap your head around. The final method is to draw the triangles from a point on a side. So rather than from a point on a vertex, a point on the side. And again, you just have to think about how many triangles do you get and what do you have to subtract at the end because you don't want it included. Obviously, we don't want the angles on halfway down a side included in our final angle sum. You end up with the same formulae whichever way you do it. I don't think these ones are going to these methods will particularly take off, but they all give us the same answer. And the two most commonly taught methods are the exterior angles method and the n-2 by splitting it up method, but those two things are normally taught side by side, so teachers don't normally choose one or the other, but they do choose both. Right, after I wrote the book, I thought about another way of doing this, and now I've changed the way I teach it, and this was after I wrote the book, so it's not in the book. And what I taught this year, I had a fairly low attaining group of Year 9 students. They're set 4 out of 5. Fantastic class, but I thought, how am I going to scaffold this? How am I going to structure it? What are they going to forget? Are they going to forget the n-2 times 180? How can I help them remember? I didn't want to do the splitting up of the polygons into triangles exercise. I'm just a bit bored of that. I want to try experiment with different ways of teaching things. So this is what I did. I said, well, here's a triangle, and we know that the angles in that add up to 180. If I stick another triangle to it, so I've joined two triangles together, I've got a quadrilateral there, 4-sided shape. Now I take that quadrilateral and I stick another triangle onto it, and then I take that shape and stick another triangle onto it. And look what I've got. I've got a triangle, I've got a quadrilateral. This one became a pentagon. So when I took a quadrilateral and I stuck a triangle onto it, I got a pentagon. And this one's a hexagon. So when I took a pentagon and I stuck another triangle onto it, I got a hexagon. So I basically have a series of polygons, each time I stick another triangle on, the number of sides increase by 1. So if I was to stick another triangle onto my hexagon, I would get a heptagon. And if I stick another triangle onto a heptagon, I get an octagon. Every time I stick a triangle on, I get a polygon with 1 extra side. So I said, right, what do we notice about this? And obviously they all know, I mean, it's pretty clear what you notice. If you attach a triangle to a polygon, then the number of sides goes up by 1, and that can be a little bit, it's like, why aren't, if I'm putting a triangle on, why isn't the number of sides increasing by 3? Well, that's partly because, well, that is because one side is stuck onto another side, and also it's actually really hard to explain. I know what I'm talking about, but just have a think about it yourself, and I'm not going to try and explain it here because I've realised I have not prepared my explanation of that. Why is it that when you add a triangle onto a shape, this number of sides increases by 1 instead of 2 or 3? And like, it's totally logical and intuitive, but just takes a second of thinking there. Anyway, because you've added on a triangle, you have increased the angle sum by 180. And what we notice there is we get a sequence that increases by 180 every time. 180 degrees, 360 degrees, 540 degrees, 720 degrees. This is so clear and intuitive and logical to students and so easy to remember. They all know that a triangle adds up to 180 degrees, and then they know just add 180, add 180, add 180. It's a lovely clear sequence. And if you've shown them this, then it sticks in their head. They remember the adding on of the triangles. They remember how the sequence builds. And that means that I can answer a question like this by using my sequence, because I can say, well, if my number of sides, I know I don't have to draw the table out every time, but I know I can start on 3 sides as 180, and I can go up by 180, go up by 180, go up by 180, and basically I end up with 7 sides as 900 just by writing out a quick sequence. And then I can just do 900, take away all these other angles, and I've got the angle x there. So we can have students just by knowing this sequence answer angle problems like that. So they literally just have to start with what they know, 3 sides is 180, and keep adding 180 each time to get the fact they need. And I started my first lesson with year 9 with this. Now, MathsPad, by the way, again, it's not free, but for subscribers, a really nice tool for demonstrating that adding on of triangles. So it's nice to see that MathsPad also have thought of this as an alternative to splitting into triangles. It's each time you go up by a side, you've basically added a triangle on. So they have a really nice tool for this. This was my first lesson with year 9 on interior angles and polygons. So I started by saying, right, here's our table. We want to fill in all the angle sums. What do we already know? They're like, Miss, we already know that a triangle has 180 degrees. Miss, we already know that a quadrilateral has 360 degrees. We don't know the rest, Miss. That's fine, because we know 2 of them, so let's work with that. First, I got them to do some missing angle problems with the facts they already knew. So we did some triangle and quadrilateral missing angle problems. Then we came back to that table and I said, right, we need to fill in the rest of this table. Then I did that demonstration with the adding on triangles, and we established that it's a sequence where you go up by 180 every time. Then they were able to fill in the table with all the other angle sums in polygons. Okay, then I demonstrated a couple of examples where we're going to do missing angle problems and we're going to use this sequence, and then they did some practice of that. Nice, simple, no cognitive overload. All we're doing at this point is using that sequence that increases by 180 every time. So they can solve problems using these angle facts. My next lesson, I started by saying, right, so let's just recap what we did last lesson. We've got this sequence. So how would I find the interior angle sum in a 50-sided polygon? Because I don't want to keep doing plus 180, plus 180, plus 180. I said, I'm going to be here all day. And I haven't got time for this year 9. Let's find a quicker way of doing it. So we wrote out the angle sums again, and we said, oh, look, this was 1 triangle, wasn't it? This was 1 lot of 180, and this was 2 lots of 180, and this one's 3 lots of 180. Oh, there's a pattern here, isn't there? So what would a 50-sided shape be, a 50-sided polygon? And they're like, oh, it would be 48 times 180, because look at the pattern. It's always 2 less than the number of sides. So they figured that out pretty easily themselves. And then we did some practice of that sort of that angle fact, so that n-2 times 180 will always give you the angles in polygons, the angle sum. Then we said, right, what's a regular polygon? And then we said, right, now we know the angle sums, we can work out angles in regular polygons by dividing by the number of sides. And we did some problem solving with that. I'll just show you my second slide there in a bit more detail. It's a bit wordy, and a couple of them did complain. They said, "Miss, this is too much to write down. We don't really want to write this stuff down." It was a bit much writing for them, perhaps. But what this is a very scaffolded task. So this is an example of differentiation and scaffolding. They were a low attaining group, and I wanted to give them a fill in the gaps task. So it said in a 25-sided polygon, the angles add up to 23 times 180 equals. They just had to use their calculator. The next question, again, just use your calculator. In the next one, we had some gaps. What is it we're timesing by 180 this time? Oh, it's n-2, and we can look at the two examples above to reinforce that. And then in the next one, oh, I'm timesing it by 180, so I've got a different box there. And then there's some working backwards at the end. So it's a scaffolded exercise that very quickly goes on to thinking backwards. Okay, so this sort of thing it absolutely worked perfectly with this group. There's the right sort of scaffolding for them. They're also the right kind of challenge where we're thinking backwards, and they very quickly came to terms with this angle fact better than I've seen classes I've taught done in the past. And this was a fairly low attaining class who I thought might struggle, but they really smashed it, did absolutely incredible work on angles and polygons once they knew this. They did not pause in their calculations of angles to find the angle sum. If I asked them to find what the angles add up to in a dodecagon, they just instantly knew it was 10 times 180. I know that most classes can do that, but the question is, will they remember it? And I think the way I did it this time with the adding on of triangles and showing them the sequence, I kind of feel like it might stick in their heads better than the way I've done it previously with splitting things up into triangles. I don't know, but it seemed to work really well. I summarised the sort of unit with 3 key facts. I feel like it's quite overwhelming, angles and polygons, because it's like, well, if it's regular, then this, but if it's not regular, then this. So I felt like it was just worth summarising the key 3. There's 3 things that you need to know. The n-2 times 180 gives you the sum of the angles in a polygon. That the exterior angle in a regular polygon is 360 divided by n, and the interior plus exterior is 180. Basically, you can do anything with these 3 facts. And the challenge then becomes the problem solving. The challenge is then not knowing the facts, but the challenge is, how do I solve problems and use reasoning with these facts in my back pocket? So this is the knowledge that the students need. The skill then comes in the reasoning and problem solving. This is an animation by Tandy Clausen May. I want you to watch this one. It's really interesting. She starts with a triangle, and she adds a triangle onto it. She basically breaks the side of the triangle and makes that side bigger. And she shows that the 2 angles, as she did that, 2 angles got larger and 1 other angle was added. So we're talking about turning a triangle into a quadrilateral by breaking a side. I talk about adding on triangles. She talks about breaking sides. Then she shows the kind of route around, taking kind of a matchstick, the route around going through the angles of turn. So the interior angles in a quadrilateral, and she's moving through those angles, turning as she goes. And we notice that the matchstick ends facing the same way that we started with. Now I'm just showing you this because it's a beautiful animation, and I took this from a CPD talk done by Tandy at the MA conference this year in 2021, and it was such a good talk because her animations are beautiful. It was all about thinking about angles in polygons as in terms of their measure of turn, and intuitively understanding that, why things have turned the whole way and why these angle facts work. But I think she's the first one that gave me the idea of, instead of splitting a polygon into triangles, you think about either adding on a triangle, or even better, breaking a side of the polygon to make another triangle. Really interesting stuff. It's worth looking at all of her slides from that presentation, or watching it in the MA recordings if possible, because it really was fascinating stuff and just so well explained. It was a real kind of conceptual understanding being given of angles in polygons. Right, so that's I've talked about pedagogy and I've talked about methods. Let's just have a quick look at some resources. I'll be fairly quick going through these. You can go to my resource libraries on my blog to find links to these resources, but I'll just talk briefly about some great stuff that's out there. MathsPad had loads. I won't go through it in detail, but there is loads from MathsPad. They have a whole exercise just on exterior angles that works well if you're teaching specifically that. Don't sort of put exterior angles as a bolt-on at the end of a lesson. It deserves its own lesson, and there's plenty you can do on it. They have true or false questions. They have really nice sets of exercises. MathsPad always has great resources. Maths for everyone as well, really nice selections of and very clearly laid out problems with angles and polygons. Lots of space here for students to annotate diagrams, which obviously they really should be doing. Really nice set of problems from David Morse at Maths for Everyone. This is interesting. This is from a TES user called It's Matt Kennedy, and he has a series of really lovely problems, various triangles and quadrilaterals, but then moving on to other types of polygon as well. And he's saying, how many angles can you find? Now this is open-ended. This is like a goal-free problem. So rather than say, work out this angle here, it's like, well, if I give you these two polygons and this information, what else can you work out? And there's a lot of angles. That means it's really, really good for mixed attainment teaching, because you can really make this quite challenging, but there's definitely accessible to all. So it's worth looking at the whole set of questions from him on TES. This is from Transom, and this is actually from part of a online worksheet where students can type the answers in and get instant marking done, which is really helpful for if you're having to teach virtual school, or perhaps set it as a homework for students to get instant feedback on. There's a whole load of questions on Transom on angles and polygons, and this is one example where in this case the students have to work out how many sides the blue polygon has, which you can just see a bit of there. This actually really reminded me of a session I went to at a conference where we were using ATM, these kind of big polygon tiles. They're really lovely to work with, and we were doing patterns like this with these polygon tiles, and it was all to do with tessellation. If you're lucky enough to have that kind of equipment in your school, like these actual polygon tiles that you can have students playing with, then it can prompt some really great discussions about angles, and this kind of thing, like what kind of tessellations or patterns can we make using these various polygons, and why. So yeah, if you're lucky enough to have the manipulatives, then that's fantastic. This is from a website, mrorisageek.com, and this is it's really interesting here. It's like, in this particular diagram, what information can you provide to make it easy to get that angle? Like for example, I could fill in the other three angles in the green quadrilateral, and then it's really easy to get that angle. Like all I have to do is 360 subtract the other angles. But what information can you provide to make it hard to determine this angle? Well, you sort of think, well, what could I put on that, and would it be enough information? Like, what's the minimum amount of information I can provide so that I can work that out? And that really takes some reasoning. On the same website, on the same blog post, we have a polygon pile-up where students are trying to work out the angle at the top, and they're given various bits of information along the way. There's also a blank version, so they can come up with their own, and they can sort of think about what's the minimum information we need to be able to work out the angle at the top. So that's a really lovely activity. Don Stewart has loads on angles and polygons. This one's really nice. You're given the angle in the yellow rhombus, and we're asked to find the angles in the orange rhombuses, but then we're asked, are the pink shapes actually squares or not? Like, really lovely questions from Don Stewart, as always. Don has a whole post about pentagons. These are 9 congruent pentagons, and you have to know what the angles are in the pentagons. This fantastic stuff, as usual, from Don. Really, really good reasoning, and really lovely engaging activities. And more from Don, where he's saying, the isosceles trapezium that you can get from cutting off the side of a polygon, how can we find the angles in those? And then he asks to generalize. Dan Draper has a blog post that is well worth a look. It's about exterior angles in polygons, and you can see some of these are not exterior angles. However, you can get the exterior angles by subtracting 180 from some of those. Like, it's really interesting thinking stuff. His blog post is fantastic. It's got some really challenging questions in, but there's a really interesting idea of kind of looking at exterior angles in different ways and solving quite unusual problems with exterior angles. So I really recommend his blog post. Last resource I want to share is one that's one of my absolute favourites for angles in polygons. Now, this is from the Mathematics Assessment Project, which was a project, American project, that Malcolm Swan worked on, and various others, and it's got some fantastic resources. This is presented as a whole lesson, and this is absolutely brilliant stuff. I'll just talk you through the main activity in the lesson, and I love the way, by the way, that it starts with Mrs. Morgan, which is convenient given that's my name. So the problem is this: Mrs. Morgan has given her class this problem, and 4 students came up with totally different methods for answering it. And There's two parts of the activity. One is to see if you can use each of the students' methods to solve it yourself, and another one is to critique some answers given by other students. Now this is what I love about this is that there are so many ways of answering this problem. For angle geometry questions, there's never just one way. It was very rarely just one way of answering. So isn't it wonderful that there's so many different ways of answering angle geometry questions? And for this one alone, there are 4 different methods presented by different students. So just so you know, you can see how the activity works. The students, your students would be shown, right, Annabelle decided to draw a line down the middle, and then you have to then follow on from her thinking. So where does she go next with that? Carlos used exterior angles. So where would you go next with that? Brian drew a line to give a trapezium and a triangle. And where would you go next with that? And then Diane divided it into 3 triangles. So all 4 methods will give you a solution. And the challenge for our students is to work out how each of those 4 methods can give us a solution. This is a wonderful task for giving students an insight into how all these different methods will work, to have them think really creatively, like, oh, I never would have thought to do it like that. And it's just, what a great activity. And also brings together everything you've taught them in terms of angles and polygons. You've got the exterior angles, the interior angles, splitting things up, mathematician skills, like you know, the idea of splitting things up is such an important skill. It's a great activity. Really, it's a whole lesson's work there, and really, really worth spending time on. Right, I want to finish by talking about ways to enrich our students' understanding of this topic and go into a bit more depth. So basically, going slightly off the national curriculum, but you know, we can't have people say, oh, my top set are so good at all the angles questions, I'm just going to move on. Actually, it's like, no, don't move on. Do some of this really cool stuff with them. Make their knowledge of maths deeper. Make them have a really wonderful, rounded understanding of these of angle geometry as a whole, rather than just show them the bits in the curriculum. If they're really flying ahead, then don't just stop them in their tracks. So tessellation is one of the obvious ones, and you know, tessellation is something that used to be on GCSE and has now gone, but absolutely has a strong place in angles and polygons. Like, it's hard to teach angles and polygons without mentioning tessellation. You know, there's some interesting stuff here about how the word tessellation comes from originally from the word four, referring to sort of 4 corners, although obviously it doesn't really relate to 4 so much anymore. But yeah, it's from the late Latin, meaning made of small square stones or tiles, and it's you know, we can literally see them everywhere in the classroom. Oh, look, tessellation there, tessellation on the floor. And it's worth asking students, look around, where's the tessellations? And you can show them pictures like this. And when I showed my class pictures like this, we ended up talking about Alhambra, and I had a student who'd been there and had seen the wonderful tessellations that I have never seen in real life. And we talked about Escher and the wonderful art of Escher, which again some students were really familiar with. So we talked about like how their, you know, I talked about how their bathroom floor at home probably has tessellation, and you know, it's a really, really interesting discussion. Then you can talk about what makes things tessellate, and how if the polygons, when they meet at a point, if those angles add up to 360, then you won't get gaps and you won't get overlaps and you'll have tessellation. Whereas some polygons don't tessellate, you know, just if you just use that polygon. And we looked at the examples there where you're saying, look, there's gaps there, it's not working, you can't fit another pentagon into that gap, so regular pentagons don't tessellate. And there's some lovely GIFs. This is from a Tumblr blog. It's absolutely lovely, showing that an equilateral triangle does tessellate, can fill the plane with no gaps, and you can talk to your students about why and look at the angles. And a square tessellates, and again, look at the angles, think about why. And what's this? A hexagon. A hexagon tessellates like a beehive, and we can talk about why, and we can think about the angles. We have a problem when we get to pentagons. Pentagons don't tessellate. Yes, and this GIF shows it really nicely. The angles in the pentagon, you can't, you know, the 108 is problematic here. So it's really interesting to think about, you know, regular pentagons don't tessellate, but some pentagons do. If you have an irregular pentagon with the right angles, like as in angles that work, then it does. And there's not just one type of pentagon that tessellates. As far as I know, there's perhaps 15, maybe more now, pentagons that do tessellate. And it's funny when I showed my students this, and I said, people, it's so exciting, they've just discovered a new pentagon that tessellates. And someone said, Miss, why do people spend years trying to find out pentagons that tessellate? Shouldn't they be trying to like cure cancer or something? And it was a good point. It's like, this is obviously important stuff, but yeah, it's people spend years trying to find these tessellating pentagons. Is quite a funny idea to a group of teenagers, but yeah, the gifts are lovely, and they really demonstrate tessellation well. Of course, we can have semi-regular tessellations, so it doesn't have to be all the same shape. And here we have 2 different polygons that tessellate, and that leads us on to lovely questions we can ask students. So, for example, this is John Stewart, and he's saying which combinations of these regular polygons can completely surround a point, in other words, can tessellate. So, can 3 hexagons surround a point? Can 2 octagons and 1 square? This is a really lovely activity to do with students. It's really quite stretching and challenging for them, and gets them doing lots of fluency practice of angles in polygons, whilst also doing some reasoning. I'd love to go into more detail on tessellation. There is a section on Mathagon, which is the amazing website. There's a wonderful section on tessellation, and you can use Polypad to create tessellations, which if you've got time to do with your students, how amazing to get them doing that. And there's a section about Penrose, and it's so enriching. And if you've got strong mathematicians who need enrichment, this is where to go. Mathagon is fantastic. You can set it for a homework because it's basically like an interactive textbook where they fill in bits as they go through and they work through the page. It's just amazing. Really good stuff. Just wanted to mention 2 more opportunities for sort of depth that people don't normally do. So this is one from Colin Foster's Instant Maths Ideas, and he said that another idea for going to more depth could be to ask students to plot a graph, the size of one interior angle against n. And I've never done that before, and this is what the graph ends up looking like. And you can see that as n tends to infinity, think about what happens to the angle, and think about what happens to the exterior angle and how it becomes more and more circle-like. It's really interesting stuff. And I've never, you want to stretch a really strong class, get them to plot the graph and get them to talk about it and get them to discuss what's going on. Just one more thing from Colin Foster's Instant Maths Ideas on this, which is about, I showed earlier that you can split up a hexagon in all these different ways, like different variations of how to split the hexagon up, and how some of them look the same, but some, there's all different ways of doing it. Here we've got an example of splitting the hexagon in one way, splitting the hexagon another way. They both end up with 4 triangles inside, but they have been split in different ways. And so it's about thinking about if we take a convex polygon with n sides, how many different ways can we break it into triangles? And you can see these end up being Catalan numbers, and this is now beyond my knowledge of this topic. But you want to go into depth. Here's some depth. Interestingly, in my recent survey, I surveyed just under 800 Key Stage 3 teachers. Most teachers are spending 4 hours or less on angles and polygons. That's in terms of kind of how long their scheme of work allows them or recommends they should spend on it. There are some teachers spending longer, a couple of weeks on it, but most teachers are really wrapping this up in a week. I think that's really not enough. I mean, the amount of stuff I've shown you today, I can't believe anyone would now think that you should do that in a week. I've suggested a 12-lesson structure, but this 100% depends on the class you're teaching. You have to adjust the length of each section depending on your formative assessment throughout your lessons. So, for example, it might be that you do 3 angle recap lessons before you get into polygons on the previously taught angle facts that are vital prerequisites, but you might need longer depending on the class, or you might not need that at all depending on the class. Then I've got a whole lesson introducing the vocabulary around polygons and all those wonderful definitions and all that sort of thing. You might not need a whole lesson on that, but maybe you do. I've got a lesson on interior angle sums. For me this year, that was using that sequence and then working out missing angles in polygons. Then interior angles in regular polygons. So moving on from here's an irregular polygon, what's X, to what's the interior angle in an octagon, for example. Then a whole lesson on exterior angles. Then I think at that point I would do the mathematics project assessment project lesson, that wonderful lesson of looking at different methods of solving the same problem. So important. You could do a lesson on solving more complex angle problems, some of the ones that I showed you, for example, from Maths for Everyone and from Don Stewart, that take a lot of reasoning. A couple of lessons on tessellation. You could easily spend a long time on tessellation. It's such a fantastic topic with lots of great tasks to go with it from all over the internet. So I reckon, you know, a good 3 weeks on that. I'm quite surprised that a lot of people wrap this up in a week. There's lots to do if you're going to teach it in depth and if you have this amount of time available to you. So that's it from me on angles and polygons. I hope you found that helpful and interesting, and I'd love to hear from you what techniques you use, what methods you prefer, have you tried out different ways of doing things, and what resources have worked really well for you in the past.